Hi, I am Osman Rizzo. Did you know that despite the rise of electric vehicles, millions of internal combustion cars will remain on our streets for decades to come? The problem regarding the quality of life in large cities is invisible but deadly. We are breathing high concentration of CO2 and nitrogen oxides every day. While engineers focus on making engines more efficient, we are missing a huge opportunity, creating the waste that is already being produced. My project, mitigation of vehicle emissions using microalgae photobioreactors, proposes a solution that doesn't just filter pollution, it eats it. You might wonder, why hasn't this been done before? Why aren't cars growing plants in their exhaust pipes? Well, the challenge is biological limits. Exhaust gases come out at 400 degrees Celsius, which instantly kills any living organism. Previous attempts failed because they tried to adapt biology to the machine. My proposal is innovative because it does the opposite. It adapts the machine to the biology. It's a hybrid system. We're not just putting a filter, we are creating a mobile ecosystem that solves the temperature barrier. And we unlock the most efficient carbon capture technology on Earth, photosynthesis. This led me to my scientific question. Is it technically possible to integrate a biological carbon reduction system into a vehicle's exhaust without compromising the engine's mechanic? My hypothesis is that if we condition the gas temperature using a heat exchanger and circulate it through the photobioreactor with Chlorella vulgaris, a highly resistant microalgae, then we can successfully reduce the CO2 concentration and generate usable biomass as a byproduct. To achieve this, I established one general objective to design a theoretical model of this bioexhaust system. Let me explain how this system works through my three specific objectives. First, the pre-treatment. We need to drop the temperature. The gases leave the engine and enter a heat exchanger. This is a critical variable. If this doesn't work, any of this project will not work. We use water cooling to bring the gas from 400 degrees down below to 4500 degrees. Second, the reactor design. The cooled gas enters a helical photobioreactor. Why helical? To maximize the surface area for the alga Chlorella vulgaris. And third, the energy source. Photosynthesis needs light. Since the exhaust is dark, we integrate a red and blue LED lighting system powered by the car's battery. So the cause and effect is clear. The gas feeds the alga, the LEDs provide energy, and the alga break down the CO2. What can we expect from this implementation? Well, I anticipate a reduction efficiency of 40 to 60% in CO2 emissions during city traffic conditions. Additionally, the harvest biomass is not waste. It's a resource that can be processed into biofuels, creating a circular economy. To conclude, improving the quality of life in our city requires bold ideas. We don't always need to reinvent the wheel. Sometimes we just need to work without nature instead of against it.